So students, a very good afternoon to all of you. Today we are going to learn about how the electronic configuration can dictate to form the modern form of the periodic table. And in my last class actually I have told you about the history of the periodic table, the merits and demerits of Mendeleev's periodic table. And there I told you that a modification was needed to construct this modern form of periodic table. Actually, scientist Mosley in 1913 he was doing some experiment to see the effect of cathode rays in some of the metallic complexes, and there he saw that root over nu, that is the highest frequency emitted by those compounds, were actually proportional to the atomic number of the elements. It was not the atomic weight. When atomic weight was plotted, some stray points were obtained in the graph. So he concluded that atomic number is the fundamental property of any element, and that was the basis of the modern form of today's periodic table. Let us see the periodic law, that is the modern periodic law. Here it is. It says that the physical and chemical properties of the elements are periodic function of their atomic number. So remember very well, it is the atomic number. That is, when elements are arranged in the increasing order of their atomic number, similar elements are repeated after regular intervals. And let me tell you that atomic number, that is the number of protons present in the nucleus. And in a neutral atom, actually number of electrons and number of protons are equal. And the electrons are arranged in different cells in a particular manner, and that is called the electronic configuration of the element. So we can say that periodic variation of electronic configuration dictates the chemical and physical properties of the elements. And electronic configuration means here mainly the valence shell electronic configuration. And the electronic configuration of elements is actually based on the Bohr scheme and above rule. So this modern form of periodic table is also called the Bohr model. So here is the periodic table I have drawn. You can find here elements with atomic number 1 to elements with atomic number 118. So you know that here we have 7 periods and we have 1 to 18, that means 18 groups. Some blocks are here, these things. Actually, S block elements, P block elements, D block elements. And these S block and P block elements are called representative elements. And this D block element is called transition element. And other than these D block elements, there are some other elements also. They are called F block elements. They are also called as inner transition elements. Now you see that in here we have these, in group 1 we have some elements which are called actually alkali metals, and in group 2 we have alkaline earth metals. And coming to the P block, here you see you have these elements in group 18, they are called noble gases, and in group 17 you have halogens. Other than that, from group 13 to 16 we have some metals, some non-metals, and in between there are some metalloids. Metalloids are actually having properties for both the metals and non-metals. And here in between you see these are called transition metals. They are the bridge between the S block and P block elements. So this actually the transition element starts from group 3 and ends at group 12. And here you see in the period actually 6 we have lanthanide, and in period 7 we have actinide. And in lanthanide we have actually, here we have many other elements which are called actually lanthanoids, that is cerium to lutetium, from atomic number 58 to atomic number 71. And here we have elements from atomic number 90 to atomic number 10 and 3. These elements actually they belong to this group 3, and we have kept them outside because if we put all these elements here, periodic table will be very long. So generally it is the trend to keep these lanthanides and actinides outside the periodic table. These are called inner transition elements because they are present actually inside the transition series. Now we will see that what is the relation between the position of these elements and the electronic configuration of these elements. That is our main aim. So you look at here. In this periodic table, I have tried to show you this relation. You see here, I have written the S block elements and P block elements. Keep the D block elements here to make it simplify. Then you see here, hydrogen is having 1 electron. So its electronic configuration is actually 1s1. And now we go to helium, which is having the atomic number 2 and electronic configuration is 1s2. Then which element will come? Element with atomic number 3, and that is lithium. So its electronic configuration, valence electronic configuration will be basically 2s1. Then comes beryllium, which have electronic configuration 2s2. This way it goes, and here these elements are p block elements, and from here we have 2s, boron have 2s2 2p1, carbon has 2s2 2p2, 2p3, 2p4, 2p5, and this is 2p6. So here we see that in a particular period actually the atomic number is increasing and increasing by 1 unit, 3, 4, 5, 6, 7, 8, 9 and 10. And if you go group wise from top to bottom, here also atomic number is increasing, but you see the order here, it has increased by a number 2. Then because you see here hydrogen is having atomic number 1 and lithium is having atomic number 3. Then coming to sodium, there is an increment of 8, and because you see it is 3 and it is 11. Now coming potassium, here is also increment of 8, and then rubidium, it is having atomic number 37, so an increment of 18. Then cesium, 55 atomic number, so an increment of 18 again, and in francium the increment is 55 to 87, so it is 32. I'll obviously tell you about how these numbers have come, and but before that you see how the electronic configuration is dictating the position of the elements in the periodic table. Here the D block elements are present, and you see this is called the 3D block, this is called 4D block, and this is called the 5D block elements, and you have lanthanides and actinides here. These are called F blocks, and here actually 4F and 5F electrons are incorporated. So I will now tell you about these numbers, how these numbers have come. This is very important for you to learn about that. Here you see I have written for period 1. For period 1 actually you have seen you have the electronic configuration 1s1 like that, and we have elements hydrogen and helium. So the number of cells present in there is 1s only, so number of cell is 1, and you know that s orbital contain 2 can contain maximum 2 electrons, so number of electrons is 2, so the number of elements in period 1 will be 2. Now you see the next period, period 2. Here you have 1s orbital, that is the inner orbital, and along with that you have 2s and 2p orbitals. So highest principal quantum number present here is 2, and the number of electrons will be in the 2s orbital it will be 2, and in the 2p orbital it will be 6. So we have total 8 number of electrons, and that will give the increment of atomic number, means 8 will be the increment that you have seen in when I was talking in the last slide. And here you see the elements are lithium to neon. And coming to the third period, you have incorporation of 3s and 3p orbitals. and here the number of cells will be then 1, 2 and 3. So the number of cells is 3 and period number is 3, and we have again increment of 8 elements, and it is sodium to argon. Then coming to period 4, you see we have incorporation of 3D, then 4s and 4p. So total number of cell will be 4, 1, 2, 3, 4, and this is 4 also indicates the highest principal quantum number present here. So in 3D we have 10 electrons, and then in S we have 2 electrons, and in P we have 6 electrons. So 18 elements will be increased actually. So it will be potassium to krypton. Then coming to period 5 also will be having the same number of elements, like because we have orbitals 4D, 5s and 5p. So 10 plus 2 plus 6, 18 number of electrons and 18 number of elements will be there from rubidium to xenon. Then coming to the 6th and 7th period, here we have incorporation of 4f orbital, and 4f orbital contains 14 electrons. So it will be 14 plus 10 plus 2 plus 6. So there will be 32 elements present in there from cesium to radon, and the lanthanides and actinides also present in these periods actually. So now you can understand from where the period number has come and why the particular period contains a particular number of elements. Now I will show you the electronic configuration of the p block elements. You know they are named as p block elements as their valence shell contains p electrons. So I am not telling you in detail, but you can look at here: boron, carbon, nitrogen, oxygen, fluorine and neon. You can see here P1, P2, P3, P4, P5 and P6 configuration, and likewise in a group you can see here this is 2p1, this is 3p1, this is 4p1, this is 5p1, 6p1 and 7p1. So they are in a group, and number of cells increased from top to bottom, and here if you go, number of electrons increase, keeping the cell number same, number of electrons increase from left to right. And here you know this from group actually period 4 to 7, these elements they are called post transition elements, because in the left side you have transition elements present in there. And here we have incorporation of lanthanides. So in these two periods, these elements are called actually post lanthanides elements. They are also post transition elements and post lanthanide elements. After p block we will see the electronic configuration of d block elements, and here they are. So here you can see you have 10 elements actually in each block of like 3D block, 4D block, 5D block. You have 10 elements present in there. In 3D you have scandium to zinc, in 4D you have yttrium to cadmium, and in 5D you have lanthanum to mercury. And if you see, look at their electronic configuration, you will see that d electrons, actually electrons are incorporated in the d orbitals. Some exceptions are there, like in chromium you have 3d5 4s1, which should have been 3d4 4s2, but you know as the stability of the half filled orbital and full filled orbital is more, so electrons are actually filled up like 3d5 4s1, and here in copper it is 3d10 and 4s1. In the 5d block you have incorporation of F4F electrons also. So this is all about the electronic configuration of the S, P and D block elements, and now you know that why they are called why they are called S block, why they are called P block and why they are called D block elements. So finally I want to tell you the general electronic configuration of the S, P, D and A block elements. So now we have learned it. Just I want to say, you see here in S block elements the general electronic configuration will be NS1 to 2, where N is equal to 2 to 7, and these are the elements present here. For example, you see beryllium, here you have the electronic configuration 1s2 2s2, and this element actually belongs to S block. And in P block I have taken an example of oxygen, whose atomic number is 8, and its configuration is 1s2 2s2 2p4. So here you can see the general electronic configuration is ns2 np 1 to 6, as is p block element, so electrons will be incorporated in the p orbital. So n is equal to, here is 2 to 7, and here are the elements. And now coming for the d block elements, you see the general electronic configuration is n minus 1 d 1 to 10 and ns 0 to 2. I have written the configuration for vanadium 23, and you see here the valence shell electronic configuration is 4s2 and 3d3. So you can match it here, and n is equal to 4 to 7, and here are the elements. And for f block, actually the electronic configuration is n minus 2 f1 to 14, then n minus 1 d0 to 1 and ns2. And look at the electronic configuration cerium. So here you see that it is 4f2 5d0 and 6s2. So you can match it here. N minus 2, that means 6 minus 2, so it is 4, and then 5d n minus 1, that means 6 minus 1, so it is 5d0, and then ns2, n is equal to 6 here. So this is all for today actually. So you have learned how we can make the total modern periodic table based on the electronic configuration of the elements. So learn it very well, and I hope you will be able to answer the questions regarding this part, and thank you for today.